Let's prove this statement. For any integer n squared plus 5 is not divisible by 4. So we start by writing proof. Since we're proving a universally quantified statement, we're going to instantiate n as an arbitrary integer. The goal is to prove that n squared plus 5 can be written as 4 times some quotient plus some non-zero remainder. The goal is to show that n squared plus 5 equals 4 times some quotient plus some non-zero remainder. If the remainder were 0, then n squared plus 5 would be divisible by 4. So either n squared plus 5 equals 4q plus 1, or n squared plus 5 equals 4q plus 2, or n squared plus 5 equals 4q plus 3. Basically, we have to show that one of these things is true. The problem here is that with all three of these cases, we need to somehow factor out a 4. But where are we going to factor out a 4 when we have a quadratic n squared plus 5? Well, that gives us a hint as to how we should approach this. With n squared plus 5, we can't factor this quadratic, but maybe we can readjust this quadratic in a way that allows us to factor out a 4. We can write this as n squared minus 1 plus 6, which we can then factor as n minus 1 times n plus 1 plus 6. But again, we can't really factor out a 4 from here. So this trick doesn't help us in any way, and you'll find that it's very difficult to find a way to algebraically express this as 4 times some integer plus some non-zero remainder. That's going to be very difficult to do. And so we have to approach this a totally different way. We have to go back to square one. If we say let n be an arbitrary integer, we end up making the problem much more difficult to prove than it really needs to be. When we say let n be an arbitrary integer, this assumption is too broad. Instead, we need to split up our proof into two cases. We can assume n is an even integer, or we can assume that n is an odd integer. By using the definition of even and odd, we'll be able to algebraically manipulate the quadratic n squared plus 5 in a way that's clearly not divisible by 4. This sort of heuristic or strategy of approaching this problem comes with practice. So let's use these definitions to our advantage. So n equals 2k for some integer k. That's in case 1. And in case 2, we have n equals 2k plus 1 for some integer k. Now you might be saying, hey, this is a little strange. We're using the same letter for two different definitions. Now in previous videos, we've used different letters when using different definitions. But this is where I want to clarify that when you split a proof into cases, then that means your assumptions are mutually exclusive, meaning that it's impossible for both of these assumptions to be true at the same time. Either n is even or it's odd. It can't be both. And so because of that, it's impossible to be defining n as both even and odd at the same time because we've split this up into two cases. And for that reason, we can treat each of these proofs as separate proofs from the whole general proof. The entire proof is understood by combining these two cases into one proof. But each case in and of itself is a proof. And the assumptions in each case are mutually exclusive. So for that reason, it's perfectly acceptable to use the same letter. Now, if you don't feel comfortable, it's perfectly fine to also use a different letter. But by using the same letter, you tell the reader that you're aware of when to use the same letter and when to not use the same letter. So I'm going to use the same letter to let the reader know that. Okay, so starting with case 1, n equals 2k, we can use substitution to plug that into n squared plus 5. So by substitution, n squared plus 5 equals 2 squared plus 5. And we can simplify this using algebra. I'll put equals here, but underneath the equal symbol, I'll put ALG as a justification for why this equality is true. So we can distribute this exponent to each factor here. 2 squared is 4, and k squared is k squared. And then plus 5. Now we're getting somewhere. Now in this expression, we have a factor of 4. And so let's use this to our advantage. We have 4 times some integer plus some non-zero remainder. Now the problem is this remainder is too big, because when dividing by 4, using the quotient remainder theorem, we get a remainder that's between 0 and 3. And so I'm going to use the quotient remainder theorem on 5 using d equals 4 to split 5 into multiples of 4 with a remainder. So this is equal to 4k squared plus 4 plus 1. And now I have a multiple of 4, which will help me when factoring out of 4. And I have a remainder of 1, which is small enough for the quotient remainder theorem. So this is the same justification algebra. And again, through simplification, we could factor out of 4 and write this as 4 times k squared plus 1, and then plus 1. So next, we need to ensure that k squared plus 1 is an integer. So we're going to let q, which stands for quotient, this is going to be k squared plus 1. Now, since integers are closed under multiplication and addition, then q is an integer, and n equals 4 times q plus 1. By the quotient remainder theorem, n is not divisible by 4. So that's the proof for case 1. Now let's get to case 2. We're going to use the same trick, but the algebra is going to be a little bit different this time. So then by substitution, then q is an integer, and n squared plus 5 is equal to 4 times q plus 1. And from here, we've shown that n squared plus 5 is 4 times some quotient plus a remainder of 1. So now we could say by the quotient remainder theorem, n squared plus 5 is not divisible by 4. Now let's move on to case 2. Case 2 is going to look a lot like case 1, except now n equals 2k plus 1, but we'll show that that won't matter. So just like case 1, we're going to use substitution. We're trying to show that n squared plus 5 is not divisible by 4. So let's see how we can express n squared plus 5 differently so that it's clearly 4 times a quotient plus some non-zero remainder. So if we plug in 2k plus 1 into n, we can rewrite this as 2k plus 1 all squared and then plus 5. We can rewrite this as 4k squared plus 4k plus 1 plus 5. And we can continue on with the simplification to rewrite 4k squared plus 4k plus 1 plus 5. We need a non-zero remainder here. 1 plus 5 is 6. 6 is too big when we use the divisor of 4, but we can split 6 into a 4 plus 2 so that we can factor out a 4 and have a remainder of 2. So let's rewrite this as 4k squared plus 4k plus 4 plus 2. And now we can factor out a 4. So once again, by algebra, this is 4 times k squared plus k plus 1. And then plus a remainder of 2. So next we're going to let q equal this quotient here, k squared plus k plus 1. So first we need to justify that by closure of multiplication and addition, q is an integer. So that means that n squared plus 5 is equal to 4 times q plus 2. So then by the quotient remainder theorem, which I'll write as QRT, n squared plus 5 is not divisible by 4. Now, since any integer is either odd or even, the combination of these two cases prove that the statement is true for any integer n. Thanks, everyone, and I'll see you in the next video.